Hello, this is Dr. Gardner. We're going to continue looking at how to classify chemical reactions. Now, I'm expecting you still have a background in writing chemical formulas, understanding phase labels, be able to write and balance chemical equations, and be able to classify chemical reactions from our first part of these discussions in part 1 of classifying chemical reactions. We're going to continue using our skills here to classify types of chemical reactions, but we will also be looking in greater detail at double displacement reactions that involve precipitation of insoluble ionic compounds. We'll review solubility rules, which you should memorize, as well as looking at how to recognize precipitates when we look at a chemical compound or looking at a chemical reaction. Then we'll go back and review a little bit on how to classify some different types of chemical reactions we've been talking about, as well as looking at some space-filling models that are simulating chemical reactions and seeing if we can recognize the type of chemical reaction from the models as well. Hopefully this will all help you on your homework for the chapter. Now, first of all, let's define what a precipitation reaction is. A precipitation reaction is a double displacement reaction. And if you recall, a double displacement reaction has the form of compound A and B reacting with compound CD. And remember, we used an analogy to say it's kind of like a barn dance where the cations and anions are swapping their dance partners, where cation A would end up paired up, instead of with anion B, ends up paired up with anion D. And then we end up with cation C paired up with anion B. So we end up in a double displacement reaction having this type of situation. Now, if I have a precipitation reaction that's a double displacement reaction, one of these two products, so one of these products, not necessarily both of them, but at least one of them will end up being a solid. So we're going to end up with one insoluble compound. So one compound will be insoluble here. And so that's what we're really looking for in a precipitation reaction. So first of all, we need to maybe define what a precipitate is. It's an insoluble ionic compound where the cations and anions, their charge attractions, are strong enough and they're stable enough in their ionic lattice that it's very difficult for water molecules to remove those ions and dissolve them by surrounding the ions by water molecules and allow us to produce a thermodynamically stable solution. So in those cases, most of the ions end up staying in the ionic lattice as a solid, and so we can see precipitates that are occurring sometimes when we mix solutions of ions. So both solution AB that has a soluble ionic compound and solution CD that has a soluble ionic compound, if we swap cations and anion pairs, sometimes we might end up with a precipitate that is insoluble because of the new pairing of cations and anions. And so a precipitation reaction, we'll see a solid start to form from our solution. And sometimes we'll notice a precipitate because the solution will look hazy. What's happening there is you may end up with really fine sized particles of the precipitate starting to form. The ionic lattice is beginning to form on a very small scale. We can end up with colloidal sized particles, and colloidal sized particles, if you recall, are in the nanometer to micrometer range usually. They're very small particles. The random motion, called Brownian motion, of our particles in solution tend to keep the small colloidal sized precipitate mixed in solution and suspended, and then we end up having light being scattered, so that causes the solution to be hazy. So a lot of times you can hold your test tube up to the light in the room and you can see this scattering of light, this haziness of solution that often indicates a precipitate is starting to form. If you give it time, the crystalline lattice, that is the ionic compound, starts to become larger as we form more precipitate, or sometimes we have the particles of the precipitate clumping together and we end up getting larger particles that start to settle. So if you give it time, you soften, we'll see solid settling on the bottom of your test tube. But realize that initial haziness of solution where you can't see through the solution, that is scattering of light that we call the Tyndall effect from those small particles in the colloidal range. So that's kind of what we're looking for, and we've all seen that because we've seen how milk is hazy and milky, right? Because we end up with colloidal sized particles of fat globules and proteins that are scattering light in milk. So we've all seen that. It just can happen to a slightly lesser scale sometimes when a precipitation reaction begins. So I start to look for those types of things. Now, in order to predict precipitation reactions, there's a few things you can realize. If you have very strong attractions between the cations and anions, sometimes that can result in precipitates forming. For example, if I have very large charges on my cations and anions, that may favor precipitate formation. Or if I have very small ions that can approach closely to one another, that can produce precipitates. So if you get highly charged species that are very small in their radius, very small in their size, that can approach closely to one another, oftentimes their attraction, their charge attraction, that we also call a Coulombic attraction, due to Coulomb's law, where the proximity and magnitude of the charges determine the strength of the attraction. Well, in those cases, we can say that we tend to get less solubility of those ionic compounds that are more likely to be insoluble. But to help you remember whether compounds should be soluble or insoluble when we're forming ionic compounds in solution, we can use a set of solubility rules. So it's very important you begin memorizing your solubility rules. I recommend you quiz yourself. If you want to, you can use a program on your smart devices to set up some flashcards to memorize yourself, or you can use the old-fashioned method. You can go ahead and get some index cards and write down solubility rules and keep quizzing yourself about what's soluble and what's insoluble. But the solubility rules you need to memorize in our textbook are on page 189 in table 5.4, and I don't really expect you to be able to read on this slide all the solubility rules very easily because of the small print, but I'm going to break up these solubility rules into two classifications. The first set we're going to talk about at the top here are when species are usually soluble, and we'll talk about any exceptions to that. And the bottom of this slide, we're looking at different anions that can be insoluble when they're paired up with cations, depending on what the cation identity is. So the bottom half is showing you things that are usually insoluble, but the exceptions where they might be soluble. I think that's a little confusing to look at them all at once in one single table, so I'm going to break these up into two tables to discuss. So first of all, let's look at ions that tend to be soluble and any exceptions there might be to that rule. So what you can expect is that alkali metal ions, so like lithium, sodium, potassium, rubidium, cesium, francium, they all tend to be quite soluble. And in most cases, especially in Chem 101, we can predict the alkali metals are going to be soluble. So if I see sodium or potassium as alkali metals, I can expect they're quite soluble, but I also would expect rubidium and the other alkali metals to be soluble too. Sodium and potassium tend to be very common cations in ionic compounds, so if I see those as part of my formula, I expect that's a fairly soluble substance. If I see the ammonium cation, I also expect it to be very soluble. Okay, so in those cases, we're going to predict for Chem 101 that they're always going to be soluble whenever they're paired up with an anion. So for example, I could have ammonium nitrate or potassium sulfate or sodium phosphate. In all those cases, because of the cation, sodium, potassium, or the ammonium cation, or any other alkali metal I might see, I expect they're fairly soluble. Okay, now, if I see the nitrate anion or the acetate ion. And remember, the acetate ion can be written a couple of different ways. We could also write the acetate ion as C2H3 O2 negative, or sometimes you'll see it written as CH3 COO negative. So if I see this acetate ion written in any of these ways in my chemical formulas with a cation that's associated with it, I can expect that it's very soluble. Or if I see nitrate with any of my cations, I expect they're very soluble. So whenever you see nitrate-containing salts or acetate-containing salts, predict that you're going to have a soluble ionic compound that should be dissolved in water. So they're not forming a precipitate in this case, if I have those paired up. Now, if I see sulfate, now many sulfates are soluble, but not 100% of them. So predict that sulfates are soluble unless we have them paired up with barium, strontium, lead-2, calcium, mercury-1, or silver. Okay, so if I see those situations, I would expect that they would form a precipitate. The other sulfates we might run into, we would expect to be soluble. So if I see a sodium sulfate or potassium sulfate or ammonium sulfate, very soluble, because both the cations we predict to be very soluble and the anion paired up with other cations we expect to be very soluble. So you're noticing that we're seeing, as we hit the alkaline earth metals at calcium, or the alkaline earth metals for barium or strontium. So as we're going down below calcium on the alkaline earth metals, we expect the sulfates to start to become insoluble. Okay. We also, as I said, the mercury 1 and the lead 2 and silver sulfates tend to form precipitates as well. So you're going to have to memorize those exceptions. You'll run into those, and I expect you to recognize them. Now, if I see ionic compounds, if I see salts that contain chloride, bromide, or iodide, I expect that when I see those ionic compounds where I have chloride, bromide, and iodide paired up with cations, they're usually soluble. There are a few exceptions that you must learn. If you see chloride, bromide, or iodide paired up with silver, mercury 1, or lead 2, the X here represents the chloride, bromide, or iodide. They will form precipitates. Now notice that the mercury 1 cation, now remember when I'm looking at mercury 1, when I have Hg 2+, it will precipitate with any of these halides, chloride, bromide, or iodide. However, mercury 2 we predict to only precipitate with iodide. So if I were to add chloride to a solution that contained both mercury 1 and mercury 2, and I added chloride, I could actually separate these two ions. Because what I would see would happen is that the chloride ion would precipitate with the mercury 1 cation, but not with the mercury 2. So I'd end up with mercury 1 here. Sorry. Mercury 1 here would end up forming the mercury 1 chloride precipitate. So I'd show a phase label that indicated it formed a precipitate, but I'd end up with leaving the mercury 2 cation in solution, so I would put a phase label with the ion of AQ for an aqueous-based solution. So I do expect you can recognize your phase labels from our previous discussions. So that's what I'm seeing here. So what we're discovering is I can use solubility rules to separate different ions. This would be a way I could separate out mercury 1 from mercury 2. I could precipitate out the chlorides and leave the mercury 2 in solution while the mercury 1 has been removed as that solid precipitate. So these are techniques we can use to often separate compounds as using solubility differences. Okay, so I do expect that you memorize these exceptions and be able to recognize them on our next exam. Now let's consider ions that are usually insoluble and the exceptions where they might be soluble. So the next slide will be when we have ions that are usually insoluble, but you must learn the exceptions. So if I see silver-containing compounds, silver-containing compounds that are ionic tend to be insoluble unless I have some of my soluble anions that we've already discussed. So if I see silver cations with nitrate or perchlorate, then we're going to see that those compounds are soluble. So silver nitrate and silver perchlorate are soluble. Or if I see silver acetate, so this is the acetate ion, which remember we can write a couple different ways, those are soluble. The silver acetate is only slightly soluble, so it's kind of borderline. But if I see other silver salts, they're going to be insoluble. In fact, remember, if I see silver chloride, if I add chloride to it, I'm going to see a precipitate. Okay. So if I look at some other anions that tend to be insoluble, we consider that if I see oxides or hydroxides, I expect them to be insoluble in many cases. So with most cations, they're insoluble. However, if I pair them up with the alkali metals, remember we already said on the previous slide that alkali metals like lithium, sodium, potassium, rubidium, cesium, they tend to be soluble, we predict. So if I see sodium oxide or sodium hydroxide, they're going to be soluble. They might react in some cases, but they are soluble. If I see some of the alkali metals, so if I see barium, strontium, or calcium, so if I look at calcium go down to barium, they're somewhat soluble. And in fact, if I see species I recognize as my strong bases, I would categorize those as soluble always. But in all other cases other than the alkali metals, barium and strontium and calcium hydroxides, we expect oxides and hydroxides to be insoluble. For example, if I form rust, iron 3 oxide, we expect rust to not be significantly soluble. Okay, if I form tin 2 oxide, I expect it to be insoluble. If I form lead 4 hydroxide, I expect it to be insoluble. Okay, if I form rubidium hydroxide, well, rubidium's an alkali metal, so I expect that the rubidium hydroxide is very soluble. Okay, so that's kind of what we're looking at here. So try to remember when these would be insoluble and the exceptions when they would be slightly soluble or considered soluble. Now, sulfides tend to be insoluble as well. So I predict that when I have cations paired up with sulfide, they're going to be insoluble unless I have sodium sulfide, potassium sulfide, ammonium sulfide, or the other alkaline earth metal sulfides. Okay, so all other sulfides would be insoluble except for those exceptions. If I have chromate, chromate tends to be categorized as insoluble unless it's paired up with some of my alkali metals or a few cases. So if I have sodium chromate, potassium chromate, or ammonium chromate, we already memorized that these should be soluble, right? So I knew those from learning my last list on the previous slide. So if I pair those up with any anions, I expect them to be soluble. So with chromate, again, they're soluble. If I get magnesium, calcium, aluminum, or nickel 2 chromate, we also expect those to be soluble. So those are situations. Now, any other cations we expect to be insoluble. So you're going to need to start to memorize these exceptions and learn the rules. Like I said, those flashcards will be really helpful, so you should start working on those right away. Okay, now if I have carbonate, phosphate, sulfite, or in this case, silicate. In those cases, if I have carbonate, phosphate, sulfites, or silicates, those are all insoluble. So I expect they're insoluble. The exceptions would be if I see them paired up with like sodium, potassium, other alkali metals, or the ammonium cations. Then they could be potentially soluble. But in all other cases, we expect them to form precipitates. So if I see, let's say, calcium carbonate. So calcium is not on my exception list, so I expect that calcium carbonate would form a precipitate. In fact, it's a precipitate that forms from hard water buildup. Other precipitates that form from hard water buildup would be magnesium carbonate or iron 2 or iron 3 carbonate. So those will all be insoluble based on our solubility rules here. Now I can still get sodium carbonate in solution, and that would be soluble, or potassium carbonate or ammonium carbonate, but any other cation we're predicting here would be forming a precipitate. So let's try to predict some soluble and insoluble compounds. So let's look at the following list of compounds and try to predict whether they're soluble or insoluble. So if I see potassium nitrate, if I'm trying to decide if it's soluble or not, I think about the cations and anions that are paired up. The potassium cation we characterize as a soluble cation. In fact, our rules were that we expect all potassium salts to be soluble in Chem 101. If we look at the nitrate anion, we also learned on our first slide of rules for solubility that it should always be predicted to be soluble as well. So since I have a cation that's very soluble and a nitrate ion that's very soluble, together we expect this to form a very soluble ionic compound. So if I were to add a phase label in a chemical reaction, I would show a phase label of an AQ here to indicate solubility. Now if I pair up these two ions, and be careful that you can recognize these. I have the ammonium cation here, and this is the acetate ion. Now, as you recall, we predict all ammonium-containing salts to be soluble. We predict all salts that have the acetate ion to be soluble, so we categorize this as a soluble ionic compound, so I could add as a phase label in chemical reactions of aqueous AQ to indicate it's a soluble ionic compound. Now, if I have calcium in my ionic compounds, we didn't have any rules that said that it was always soluble. So there's going to be cases where calcium salts can precipitate, just like when we said calcium carbonate can precipitate, right? Or we could expect that calcium phosphate, calcium sulfate would precipitate. We can also expect that calcium hydroxide would be soluble based on our previous rules, so I have to know my rules for those. But chloride, we know chlorides are usually soluble. The exceptions are if I have silver chloride, mercury 1 chloride, or my lead 2 chloride. Those are the only chlorides we learned should precipitate. So in this case, I expect calcium chloride to be soluble. Now the next species we see is sodium hydroxide. Now all sodium salts we predict to be soluble, so right away I can tell this should be a soluble compound. Also, if I have a strong base, I expect all strong bases to be soluble. So if I see sodium hydroxide, for those reasons, it's a strong base on my strong base list that we were working on, and the sodium salts are all soluble, we predict this is soluble. Now the next species we see is iron 3 hydroxide. Now if you recall, oxides and hydroxides were in our frequently insoluble list, so we expect they usually will form insoluble compounds. The exceptions are if I have an alkali metal with my hydroxide, then it would be soluble, so like sodium or potassium hydroxide. They're strong bases as well, so they'd be soluble. However, if I get iron 3 hydroxide. Well, iron was not on my exceptions list, so we expect that the iron 3 hydroxide would form a precipitate. So in a chemical reaction, I would put a phase label of an S. So it's very important to be able to predict whether I form a precipitate or a soluble compound, that we learn our solubility rules. So let's practice with another list of these. So if I look at the following list of compounds and I want to predict which of the following is insoluble, well, I can see that calcium carbonate, if I look at it, well, calcium isn't on my list of always being soluble. So there's many times where calcium compounds can be insoluble. Okay, so if I also look at carbonates, carbonates is on my list of compounds that are frequently insoluble. So in this case, the exceptions when carbonates would be soluble would be with alkali metals like the sodium carbonate or potassium carbonate or ammonium carbonate. We expect in those cases it would be soluble. However, if I'm with other metal cations, we expect it to form insoluble precipitates. So calcium carbonate, as I said before, that produces basically hard water buildup. That's one of the insoluble compounds that form, so it would be a precipitate. Now, if I look at potassium oxide, well, I can look at the cation potassium and the oxide anion, and you might recognize the oxides in our solubility rules are usually insoluble. The exceptions are with some of my alkali metals. So I expect that potassium, since it's an alkali metal and we had it on our list as predicting to always be soluble, that we expect this compound to be soluble. So I'm going to put a phase label indicating that aqueous, so it would end up dissociating from its ionic lattice, and we end up with the ions surrounded by water molecules and dissolved in solution. Now, if I see calcium chloride, well, be careful because calcium ions aren't always soluble. Chloride ions are usually soluble, but there's some exceptions, right? So if I think about the exceptions for the halides, like chloride, bromide, and iodide, well, chloride will precipitate with silver cations, it will precipitate out with mercury 1 cations, it will precipitate out with lead 2 cations. So I expect in this case, since I don't have silver or mercury 1 or lead 2, I have calcium instead, this would be soluble. So all other chlorides we predict to be soluble once I learn those solubility rules. So I put a phase label and indicate that. Now here we have ammonium sulfate. So if I look at those, the cation and the anion here, well, the sulfate anion can sometimes be insoluble. Now, the exceptions to that, in fact, I expect sulfates are usually insoluble. The exceptions to that are as if I have sodium sulfate, potassium sulfate, ammonium sulfate, sometimes the other alkali metal sulfates can be soluble. If I start looking at ammonium sulfate, though, the ammonium cation was on my list. I predict it to be soluble. And the ammonium cation we also learned to predict in Chem 101 should always be soluble. So we're going to go ahead and put a phase label of AQ here. Now, if I have barium hydroxide, well, I have to be careful because sometimes barium salts can precipitate, and sometimes hydroxide salts can precipitate. In fact, we expect hydroxide salts are on my usually insoluble list. The exceptions are that barium hydroxide, strontium hydroxide, and calcium hydroxide will be soluble. In fact, I can expect any alkali metal hydroxide to also be soluble. So if I recognize a strong base, you predict that that hydroxide is soluble. So in this case, barium hydroxide is soluble, so there's an AQ there. So I do expect, and it's very important in order to predict precipitation reactions, that you can predict whether an ionic compound is soluble or insoluble. If you do not prepare to predict solubility of ionic compounds before the next exam, you won't be able to predict the correct products of precipitation reactions. And I do plan on having several precipitation reactions on the next exam, and so it could potentially drop you a full letter grade if you were not to memorize solubility rules. So please memorize them. Let's look at one more example of ionic compounds that we want to predict solubility for. Let's consider that we have nickel 2 nitrate. If we look at nickel 2 nitrate, well, sometimes nickel cations can be insoluble. They're not on our always solubility rules list. The nitrate ions we did predict to always be soluble. So because nitrate we predict to always form soluble salts, we're going to say this is soluble. Okay, the next species is sodium acetate. So the sodium salts we predict to always be soluble in Chem 101. The acetate salts we always predict to always be soluble. So we're going to say this is a very soluble compound. Whoops, AQ there for soluble compound. If I have lead 2 chromate, well, lead salts can frequently precipitate, so I'm not sure if this is soluble or not yet, because there's cases where I can form precipitates with lead 2. Chromate is frequently insoluble, so the first thing I might want to think is, oh, I have a chromate, it's probably insoluble with the lead 2 cation. Definitely that's not one of my exceptions. The only exceptions we learned for the chromate are some of my alkali metals like sodium, potassium, my ammonium, magnesium, calcium, aluminum, and nickel 2. Those are the ones that would be soluble. So lead 2 isn't on that list for exceptions, so I expect lead 2 chromate to form. And in fact, lead 2 chromate forms a beautiful yellow precipitate. Some people will describe it as a canary yellow color. And so we end up with that beautiful yellow precipitate that forms, and so we get a solid that would come out of solution. Now, copper 2 chloride. Now, copper cations can sometimes precipitate, so I need to look at the anion. Chloride salts are usually soluble, but there are a couple of exceptions you should learn. So if I get silver chloride or lead 2 chloride or mercury 1 chloride, we end up with forming precipitates. Since this isn't on the list, we expect copper 2 chloride to be soluble. So we end actually up with it in solution because of the copper 2 cations. It makes a nice blue colored solution from copper 2 chloride dissolving. Potassium hydroxide, you should recognize that's a strong base. Remember we said strong bases should always be soluble. However, I do have to think some hydroxides are insoluble, but not with potassium. So hydroxides are usually insoluble unless we're with alkali metals like potassium, or if I'm with barium, strontium, or calcium. So if I see those ions with hydroxide, it's going to be soluble. Also, if you ever see a strong base with hydroxide, we expect it soluble. So that's what I'm looking at for the solubility rules here. Now, in my live lectures, sometimes I give eye clicker quizzes, but for you that are watching just this video, you don't need to use any eye clickers. But let's just predict a couple more solubilities here. If we end up with, let's say, silver chloride, and we think about its solubility, well, silver cations can sometimes precipitate, so I need to look at the anion. The anion, we have rules for that it should be soluble unless it's paired up with a few different metals. So unless it's paired up with silver, mercury 1, or lead 2. Now we have silver here, so I have silver chloride, so it forms a white precipitate. So I end up with a solid here. I don't expect that you can predict colors until you start observing these in the laboratory. Now, if I have mercury 1 bromide, well, mercury 1 will precipitate out with bromide, chloride, or iodide. So in this case, since mercury 1's with bromide, it's going to precipitate, so I get a solid. Now, however, if I were to see mercury 2 bromide, remember the rules are different. If I see mercury 2 bromide, well, mercury 2 will not precipitate out with chloride or bromide. It will precipitate with iodide, so I'd have to be careful. Mercury 2, we predict, based on our rules, would be soluble. I'm likely to ask you a question along these lines on the exam, so make sure you know the difference between mercury 1 solubility and mercury 2 solubility, because we can use different halides like chloride, bromide, or iodide to separate these out. Specifically, I can add chloride or bromide to mercury 1 and precipitate it, whereas I'd have to add iodide to the mercury 2 to precipitate it as a halide salt. Now, if I look at calcium carbonate nets, my calcium ions can frequently precipitate. They're not on my always solubility list. Not always soluble. My carbonate ions are frequently insoluble. So here's a case where I have to think about this. Which types of carbonates are soluble? Carbonates that tend to be soluble are going to be some of my alkali metal carbonates like sodium carbonate, potassium carbonate, or if I have ammonium carbonate, they'd be soluble. But calcium isn't on this list, so we're going to predict the forms of precipitate like we've seen it several times before here in this discussion. So there's the hard water precipitate. Let's consider if we look at my strontium sulfide. So sulfides are on my usually insoluble list, so I need to look at the cation to see if it's an exception. We expect that if I have an alkali metal, sodium, potassium, or the ammonium cation, that it's very soluble. Strontium salts of sulfide are fairly soluble. It's one of those alkali metals, so we'd expect this would be a fairly soluble salt. If I see lead 2 iodide, well, chloride, bromide, and iodide are usually soluble, but there were a few exceptions. Remember that if I have chloride, bromide, or iodide paired up with lead, mercury 1, or silver, they form precipitates. So this would be another precipitate here. So based on our solubility rules, we predict A, B, C, and E would definitely form precipitates. The strontium sulfide would be the most soluble because I have a alkali metal sulfide. Okay, so that's what we're using our solubility rules. So now, what I like to do on exams is usually give you a list of several ionic compounds like we've been going through, and I will often have you either circle the precipitates or circle the soluble ionic compounds for that question, and whether you've circled the correct compounds based on solubility will determine how many points you receive. So make sure you practice this, go back and keep practicing for different ionic compounds, get together in your study groups and quizzing each other about which ionic compounds would be soluble, while one of you is looking at the solubility rules and the other one is trying to do it from memory. These are good ways that you can practice, so I do recommend you keep studying these and work in some study groups. Now let's consider where we can apply our knowledge we just developed. If we want to look at solubility rules and apply the knowledge that we've developed, we can go ahead and use this to predict precipitation reactions. So remember, as I said before, precipitation reactions are a form of double displacement reaction where we have two compounds that start swapping their partners in the compounds. So for an ionic set of compounds, we can swap the cations to be paired up with the other anions, and then in a precipitation reaction, if we want to know if a reaction occurs or not, we see if we form an insoluble compound. Now I need to warn you, I sometimes will give you soluble salts that if we swap the partners to see if there's a double displacement reaction, that they all form soluble products. If that were to occur, we expect that no reaction has happened. So if everything to begin with is soluble and everything at the end is soluble and there's been no change in the formulas of the compounds to form anything that would precipitate, so if I don't see a precipitation reaction occurring, then we say no reaction has occurred, and you can write NR as a product for no reaction. I often will give you at least one example of a set of ion-containing solutions with ionic compounds that I can mix where no precipitation occurs on an exam. In that case, just write no reaction. So make sure you can recognize when there is a precipitate and when there is not a precipitate. Sometimes we don't get any precipitation reaction occurring at all. So let's look at this reaction and see if there's a precipitate forming. So I've written a reaction without any phase labels, and we're going to use our solubility rules to predict phase labels. So if I have lead 2 nitrate and I mix it with sodium chloride, and I could potentially swap all of my ion partners in a double displacement reaction to form lead 2 chloride and sodium nitrate, let's predict if anything would be a precipitate and what would be soluble. Is lead 2 nitrate soluble? So hopefully you remember from our solubility rules to predict that all nitrate salts are soluble. So I would show a phase label here of AQ to indicate a soluble ionic compound. If I see sodium chloride, I expect that all sodium salts should be soluble for Chem 101. And I expect that all chloride salts will be soluble unless I have chloride paired up with silver, mercury 1, or lead 2 cations. Okay, so sodium chloride, which is common table salt, right, is very soluble, so I show that it's soluble with an AQ for my label. And so I do want you to be adding phase labels for the rest of the course. Now, if I end up with lead 2 chloride, well, lead 2 cations can sometimes precipitate. Chloride ions are usually soluble unless they're paired up with a couple of different ions. Silver, mercury 1, or lead 2. So here we have a case where I have a halide with lead 2. So all of my chloride, bromide, and iodides we expect to precipitate with the lead 2 cation. So this forms a solid precipitate. So right away I know a precipitation reaction is occurring here. Now I'm also going to double check my last ionic compound to see whether it could form a second precipitate or if it's soluble. So if I have sodium salts, we predict all sodium salts to be soluble. If I have nitrate salts, we expect all nitrate salts to be soluble. So you notice I've underlined in these cases the types of ions that we expect to usually be soluble. So I see nitrate salts are usually soluble. Sodium salts we predict to always be soluble. So sodium and nitrate salts always soluble. Chloride is usually soluble, but we saw there were a couple of exceptions, right? So there are exceptions for chloride salts, so you have to know them. So everything I put a phase label as soluble that has sodium or nitrate in it, my only precipitate is lead 2 chloride. So if I rewrote this equation, I could show my phase labels indicating everything that was soluble and my precipitate. So if I want you to predict the products of a precipitation reaction, please go ahead and write phase labels so I know you predict the correct precipitate. Okay, let's review the different classifications of reactions we've looked at so far. So far we've looked at decomposition reactions in part 1 of these tutorials on classifying types of reactions. We've looked at combination reactions. We've looked at single displacement in the metal reactivity table. And now we've been looking at some double displacement reactions where we've been focusing on precipitation processes. There are other double displacement reactions. For example, we will be looking at in the next tutorial acid-base neutralization processes, which can also be classified as double displacement. So let's see if we can classify a few different types of reactions with the different categories we've been looking at. Now here I have my ammonia gas reacting with hydrochloric acid to form ammonium chloride. Now this is an acid-base neutralization reaction. I have an acid neutralizing with a base, the weak base ammonia. And if I try to classify this under the other classification categories we've been looking at, well, I want to look at the type of pattern I'm observing. And I'm actually observing a pattern here of A reacting with B to form AB. And so if I'm looking at that type of reaction, you should realize that can be classified as a combination reaction. We've combined either two elements or two simpler compounds into a more complex compound. We can say, other than a combination reaction, this is synthesis, so combination or synthesis. So you want to look for these patterns and try to do your classifications. Now my next reaction I want to classify is copper 2 chloride. And if I look at the phase labels, it's copper 2 chloride in solution. It gives a nice blue color. If I have sodium sulfide, all sodium salts are soluble, so it's in solution. We form products of copper 2 sulfide, which is precipitating. I know that from the phase label was given to me. And then sodium chloride is soluble. If I look at this, this has the pattern of AB reacting with CD here. And we're getting the copper cations A with the sulfide ion, so I get AD here, and I end up forming a CB product where my C is sodium and my B is the chloride. So you should recognize that form as double displacement, right? We swapped all of our partners here, so we can think about that barn dance analogy where we're swapping our dance partners and everybody ends up with a new dance partner. So that's double displacement that I would categorize that one as. Let's consider this reaction. If I have nickel 2 sulfite and I form nickel 2 oxide and sulfur dioxide in this case, well, I can see this as the form of A, one compound forming B and C, two products, and I should recognize that's the form that I see when I have a decomposition reaction. So when I have one species forming multiple products, that's a decomposition process, right? We could also define this as a gas evolution reaction, as we'll be seeing. I have solid going to a solid and gas. So whenever I produce a gas as a product and I didn't have any gases as reactants, we can define that as a gas evolution process. So this is a decomposition reaction and gas evolution. Okay. Here's another reaction. Here I have calcium metal reacting with a solution of lead 2 chloride, and I end up forming a solution of calcium chloride, and I get lead 2 solid elemental metal. Now we have to be careful to look at this. I don't really classify this as a precipitation reaction, and that's because I started with a solid and I ended up with a solid. So don't classify it as precipitation. And in fact, I'm not using any solubility rules here because I ended up with an elemental metal that was a solid to begin with, an elemental metal as a solid to end up with. I did not get an ionic precipitate. So be very careful. Frequently, I'll have students just look at those solid phase labels and incorrectly assume that always means a precipitation reaction. It does not. For precipitation reactions, we're looking for an insoluble ionic compound that is forming when you had soluble ionic compounds in solutions that you were mixing. So this is not a precipitation process. So I need to start to look at the form here. So I have element A reacting with compound with element B and C here. And I'm forming, as they react, a new compound that has element A paired up with element C, the chloride. Right? And I end up with element B, the lead, being displaced, right? So this is a single displacement reaction. Now you can recognize single displacement reactions because I've used the analogy before that that's somebody going to a dance stag, so they're going all alone to a dance. So calcium goes to the dance alone, steals lead's date, so we end up with calcium dancing with chloride, and lead ends up having to be a wallflower, being all by themselves. So if you see the type of scenario where somebody, an element's coming into the reaction by themselves, and they end up forming a chemical compound, and you end up with a new element by itself, that's a single displacement process with the following form. Okay, so hopefully you start to be able to recognize these. We're going to practice looking at just a few more of my reactions. Let's consider we look at the following reactions: ammonium chloride here reacting, and I have ammonium chloride reacting to form the ammonia gas and the hydrogen chloride gas. Now, since I see a solid forming gases, we can say this is a gas evolution reaction because I have gases as a product, no gases as a reactant, so we define that as gas evolution. Now be careful, if everything was a gas on both sides of the arrows, that's not really gas evolution, that's just a gas phased reaction. But here we're producing gas, so it's evolving gas, I say it's gas evolution. It did not have gas to begin with. I can also recognize this as the form of CD going to C and D, so I'm seeing one compound forming multiple products, so hopefully you recognize this as a decomposition reaction. So I should classify that as decomposition. Here we have a reaction of zinc reacting with chlorine gas to form zinc chloride. Now in this case, we would predict this to be, because I have two elements forming a compound, as being what type of reaction? Hopefully you said this would be combination or synthesis. Okay, those are synonyms for the same process. So when I see elements or simpler compounds combining to form a more complex compound, we say we have combination or synthesis. Now if I have zinc reacting with copper 2 chloride to form copper metal and zinc 2 chloride, this has the form of A reacting with CD to form free C and AD. Hopefully you recognize that this would be a reaction where we have our analogy with somebody going stag to the dance and they steal somebody else's dance partner here, and we end up with the copper metal being displaced, and we end up with zinc chloride. So this is a single displacement reaction. If I want to predict if this would occur, I use my metal activity series list that we talked about in the last tutorial. So my metal activity series list tells me that since zinc is higher on the list than copper, zinc would definitely rather oxidize. It would rather lose electrons and form the zinc 2 cation, and since copper is lower on the metal activity series list, it gains the electrons that zinc is losing. And so as we gain electrons, the copper 2 cation in this case is gaining 2 electrons. As it gains 2 electrons, it ends up forming neutral copper, and then what's happened is the zinc has lost 2 electrons to form the zinc cation, which is a positive 2 charge. Okay, and if you want to look in greater detail at when we're transferring electrons, there's a chapter later in our book that's on redox reactions, oxidation reduction reactions, and we can look at that later in the course, and we'll see quite a bit more about electron transfer. Okay, so we can call this a redox reaction because I'm transferring electrons as well. So this is single displacement though, because I'm displacing copper with zinc, and I should be able to recognize that form. Now if I see silver nitrate reacting with potassium chloride to form silver chloride and potassium nitrate, in this case where I see ionic compounds for 2 reactants and 2 products, I often will look for a possible precipitation reaction. So I use my solubility rules, and I know silver nitrate is soluble, I know potassium chloride is soluble, all potassium salts are soluble, all nitrate salts are soluble. However, even though potassium nitrate, those ions are very soluble, chloride, when it's paired up with silver, forms a precipitate. If it was paired up with mercury 1 or lead 2, it would also form a precipitate. So I should recognize that as a precipitate. Since I'm starting with everything in solution, and I end up with a solid forming from an ionic compound that is insoluble, I predict a precipitation reaction. We can also classify this as double displacement, right? It's kind of that barn dance analogy. Everybody came with a dance partner, everybody ended up with a new dance partner at the end of the process as we swap our cation and anion pairs. Okay, so I want you to recognize those types of double displacement processes. Now here's a reaction where we're looking at solutions in laboratory, and we're using our observations to predict the type of reaction that's going on. So here I have a solution that's blue, and the blue solution contains copper 2 cations. So this could be, for example, let's say copper 2 nitrate. So if I have the solution of copper 2 nitrate, And if I put in, let's say, a steel nail that has iron present, so I have iron as one of my reactants as a solid, and I'm mixing that with the solution of copper 2 nitrate, what we observe is we end up with copper metal coming out. So I end up with copper metal coming out of solution as a solid, and I'm seeing the blue color disappear from solution because I'm losing the copper 2 cations as they form elemental copper. And then some of the iron is dissolving. If we were able to see some more of the nail, some of the iron to be dissolving, and we're ending up with iron cations in solution. Whoops, ignore that. So I'm ending up with iron cations in solution. It could be iron 2 or iron 3. So let's say we're getting iron 3 cations. And I still had the nitrate, so I could get iron 3 nitrate. So really, if I were to write this reaction, I end up seeing iron reacting with copper 2 nitrate, which is soluble, and I'm forming a product that has elemental copper, right? That's coming out of solution. So I'm going to show copper by itself as a solid coming out. That's what we're seeing here. And then I form the other product's going to be my ionic compound, my iron 3 nitrate, because I had nitrate ions and I had iron 3. So I'm going to end up with iron with 3 nitrates. And nitrate salts are soluble, so I'm going to put AQ here. And I want to note, when you're working on the homework for this textbook, we usually won't show the phase labels as subscripts. They'll just be shown after the formula in brackets to get credit, so be careful with that. So if we're looking at this, we can see this has the form of A reacting with BC to form B plus AC. So this is a single displacement reaction we're observing. Okay, so that should be classified as single displacement. Now, this tutorial at this point is long enough that I think I'm going to stop. I'll do another mini tutorial that will look at classifying types of reactions based on looking at molecular models. But this is where we'll stop for this session. Have a great day, everybody.